Hi everyone, welcome back to Sage 101. I am Dane, an AVP for academics, and today we'll be talking about one of the most essential and foundational topics in Physical Chemistry 2 or FICHA 2, and that is chemical equilibrium. So I'll walk you through both the concepts and a couple of sample problems, and I'll be annotating along the way. So feel free to follow my thought process as we go. So let's begin first with the basics. What is chemical equilibrium? It is the state in a chemical reaction where the rate of the forward reaction equals the rate of the reverse reaction. And this is what we call as dynamic equilibrium. Dynamic because the reactions are still happening, but they're happening at equal rates, so the concentrations of all substances involved stay constant over time. And it is also direction independent. That means you can start with reactants and move forward, or start with products and move in reverse, or even do both at the same time, and you'll still eventually reach the same state of balance. So at this point, the composition of the system remains constant, although reactions are still occurring, just at equal rates. Now let's draw a distinction between chemical equilibria and phase equilibria. Chemical equilibrium refers to a situation where the reactants and products coexist in a reversible chemical reaction. Phase equilibria, on the other hand, deals with different physical phases being in equilibrium. So for example, when a liquid and its vapor are in balance. So it's important to differentiate the two because while they share some principles, the systems involved behave differently. So at the heart of equilibrium lies the concept of Gibbs free energy. This is the maximum net energy available to do work in a system, and it's represented by the equation G is equals to H minus Ts, where H is enthalpy, T is temperature, and S is entropy. So when a system reaches equilibrium under constant temperature and pressure, the change in Gibbs free energy, or delta G, is equal to 0. So in other words, delta G is equal to G of products minus G of reactants equals 0. And this is one of the key thermodynamic criteria that tells us that the system is at equilibrium. Now let's look at how equilibrium responds to changes in its surroundings. So according to the Le Chatelier's principle, when a system at equilibrium is subjected to a disturbance such as a change in concentration, pressure, temperature, or even volume, it responds in a way that minimizes the effect of that disturbance. So for example, if we increase the concentration of a reactant, the system will shift toward the products to consume that extra reactant. If we increase the pressure, the reaction will shift toward the side with fewer moles of gas. If temperature increases, the system shifts in the direction that absorbs heat, and that is usually the endothermic direction. Also, when dealing with dilute solutions, there is a special case where the ratio of concentrations of two species, say component B to component A, equals a constant value K, and this is known as the distribution coefficient or partition coefficient, and it tells us how a solute distributes between two phases in dilute conditions. Now that we've covered the core concepts, let's apply them in a sample problem. Here's the first one. The equilibrium constant for the reaction A plus B yields Y plus Z is equal to 0.1. If we start with 3 moles of B, how much A should we add so that we end up with 2 moles of Y at equilibrium? So our goal here is to find the initial amount of A, or N sub A, that gives us exactly 2 moles of Y once equilibrium is reached. This is a perfect opportunity to set up an ice table. So initially, we have N sub A moles of A. So what's N sub A? We'll find out later. Then 3 moles of B and none of the products. As the reaction proceeds, 2 moles of A and B react. since we want 2 moles of Y formed at equilibrium. That means the change in A and B is -2 or -2, and the change in Y plus Z is +2 or +2. So at equilibrium, we're left with n sub A minus 2 moles of A, 1 mole of B, and 2 moles each of Y and Z. Now we plug these values into the expression for the equilibrium constant, and that is K is equal to products over reactants. That becomes K is equal to 2 times 2 over quantity of n sub A minus 2 close quantity times 1. And this expression is equal to 0.1. Solving this, we get n sub A will now be equal to 42 moles. And that's our answer. It may seem like a lot, but remember that equilibrium constant is quite small because the reaction favors the reactants in this case. So we need to add a lot more A to push the reaction toward the product side. Now let's move on to our second problem, which involves the iron thiocyanate system. The balance reaction is iron 3 plus thiocyanate ion in equilibrium with the iron thiocyanate 2 plus complex, and we're told that the equilibrium constant for this reaction is 1.2 times 10 to the power of 3. So we're mixing 0.02 moles of iron nitrate with 1.0 liters of 0.1 molar potassium thiocyanate. So the question is, what are the equilibrium concentrations of iron 3 plus thiocyanate ion and iron thiocyanate complex? So to solve this, we'll set up an ICE table. Again, initially we have 0.02 molar iron 3 plus and 0.1 molar thiocyanate ion. There is no product present yet, so the initial concentration of the iron thiocyanate complex is 0. Now let's say that X amount of the reactants reacts to form the product, and that means the change in concentration for both iron 3 plus and thiocyanate is -X, while the change for the complex is +X. At equilibrium, the concentration of iron 3 plus is 0.02 minus X. The concentration of thiocyanate is 0.1 minus X, and the concentration of the product iron thiocyanate is X. We then plug these values into our expression for the equilibrium constant. This gives us X divided by the product of 0.02 minus X and 0.1 minus X, and that's equal to 0.2 times 10 to the power of 3. So when we solve this equation, we get two possible values for X. One of them is 0.1 and the other is 0.0198. Only the second one makes sense because if we use the 0.1, it would leave us negative concentrations, which isn't really possible in reality. So we go with X equals 0.0198. Now that we know X, we can calculate the equilibrium concentrations. The concentration of iron 3 plus is 0.02 minus 0.0198, which equals 0.0002 molar. And the concentration of thiocyanate ion is 0.1 minus 0.0198, which gives 0.0802 molar. And the concentration of the iron thiocyanate complex is simply X, so it's 0.0198 molar. Finally, let's not forget about the Van 't Hoff equation, which expresses how the equilibrium constant depends on temperature. So as temperature changes, K changes too, and understanding this helps us predict how the equilibrium position will shift under thermal stress. And that wraps up our tutorial on chemical equilibria. So we explored what equilibrium really means, how to analyze it, and how to solve problems with ICE table. and how equilibrium systems respond to various changes. So just remember that equilibrium is all about balance and system response. I hope this helped you gain a clearer grasp of the topic, and thank you for watching this video and happy studying.